2, 1. All right. Welcome to Math 389 Advanced Analysis. This is what we will consider as Lecture 3. And so I wrote down 4 things that I wanted to talk about today. So the rearrangement theorem, sniffing out formulas, sums of squares, and integrals and limits. So out of curiosity, you can jump over things. Or we can maybe move some of the desks if you want, so you can walk behind. How many of you know the rearrangement theorem? Do you do this in real analysis? So if I give you a sequence, A1, A2, A3, dot, 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 does it matter the order we sum? It would be wonderful if we could just sum the terms in any order we want, right? What do you think?
Well, sometimes it matters.
Sometimes it matters, right? And so one of the purposes of this class is, advanced analysis is talking about when does order matter? So for example, we could say, Hn is the nth harmonic number. It's 1 plus 1/2 plus 1/3 plus 1 over n. Does the sum n go from 1 to infinity of 1 over n converge or diverge? What do you think? Diverge. How would you prove it diverges? Lots of ways, almost enough ways for everybody in this classroom right now to have their own way of proving it. How could you prove that this sum diverges? Oh, come on in. Yeah.
I will have to find a path.
Yeah, come down here. It's like Price is Right. So how would you prove that the harmonic series diverges? Okay. And what does that mean? Is that looking at like the 2 to the nth term?
Yeah.
So you could use some advanced series tests like that. Good. What else could you do? There's lots of ways. Almost any way you choose. I mean, this sum diverges. I thought you had a way.
Did you say
Yes.
you could find something less than it that diverges?
Good. You could find something less than it that diverges. What can you find less than it that diverges?
You can use integral test.
So you could use the integral test from calculus and show that this is going to be dominated by like an integral of 1 over t. And it even gives you some rate about how quickly it diverges. Here's a fun way. Assume converges. And let's reorder. So we have 1/2 plus 1/4 plus 1/6 plus 1/8 plus 1 over 1 plus 1 over 3 plus 1 over 5 plus 1 over 7 plus dot dot dot. And let's call the sum S because we have absolutely no originality. So this is the sum S. What can you say about the sum of the evens? So what would we know about the sum of the reciprocals of the even numbers? Not 1. I'm sorry? It's less than the sum of the odds, because we're assuming it's finite. But you know something about the sum of the reciprocals of the evens. It's 1/2 times S. So you get S equals 1/2 S plus, what do you know about the sum of the odds? So somebody already said something about the sum of the odds versus the sum of the evens.
Well, it's greater than.
Right? Plus this over here is greater than 1/2 S. Right? Because if you look term by term, 1 is better than 1/2, 1/3 is greater than 1/4, 1/5 is greater than 1/6. So if it converges, I've just got a bunch of positive numbers, I can just put all the evens together and all the odds together. So I would get that S would be strictly greater than 1/2 s plus 1/2 s, which is just s, which is a contradiction. So this is, a nice way of showing that the harmonic series diverges. Another good way to show that it diverges is group it in blocks of length 2 to the n, where n is growing. And so if you group it that way, you have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 all the way up to 1/8. When we look at blocks like this, 1/9 to 1/16, each of these blocks is at least 1/2. And it's a nice exercise, you can go through and you can get upper and lower bounds for, summing, a certain number of terms of the harmonic series, and you can actually get that it's growing like the log of n. So the rearrangement theorem says the following. So how many of you have never heard or seen the rearrangement theorem from analysis? Okay, so the rearrangement theorem says if the sum of an converges conditionally, but not absolutely, you can rearrange so that the lim sup and lim inf are whatever you want. So because it converges conditionally, but not absolutely, let's assume the ANs are all real, must have the sum over all n such that AN is less than 0 of AN. What must that sum be? So if I sum over just the indices where AN is negative, what must be true about that sum? It's negative. How negative? Is it possible both of these numbers are finite? Okay, why can't they both be finite? So at least one of them is infinite. Is it possible that just one is infinite and one is finite? So is it possible that one is infinite and one is finite? Why not? Otherwise, it won't converge conditionally. So I know the first one has to be negative infinity, and the second has to be positive infinity. So somebody give me a number that they like. 16. And I assume you chose 16 because it's 1 less than 17, which is a really good number, right? Somebody give me a number greater than 16. 17. So what we can do is we can keep adding terms. Oops. We can keep adding terms until our sum first breaks 17. So we just keep taking indices, starting with the smallest index we can until we first break 17. And then we take indices and we such that the things are negative, and we keep doing it until we first get below 16. And then we just keep going like this. And so I'm not going to go through all the details, but hopefully this is enough for you to get a sense of why the rearrangement theorem is true. Because the sum converges, I do know that the ANs have to be going to 0. So because they go to 0, I can order them in decreasing magnitude of the positives and decreasing magnitude of the negatives. And I just keep taking the positives until I first break 17. And I have some idea of how much I can break it by. Then I go below 16. And then when I break it, it's possible that I might break it by more the next time, but I can't be breaking it by too much more. And eventually that's going to have to be done. Now, writing this down rigorously is not necessarily fun, but this is hopefully enough of a argument that you can see. We have to be careful. So one of the big rules is infinity means danger. Whenever you see an infinity, you must be careful. We can't just move the summons around however we wish. That's sad, right? Okay, so that's one thing. I wanted to do, I think, integration, sniffing out formulas. So we'll do sniffing out formulas next. Some of you have seen me do, I think, sniffing out the product rule. Yes? So we'll sniff out 2 formulas. The hardest thing in math is to try to figure out what to prove. A lot of this can come down to trying to figure out what's a good quantity to study, what's a good thing to define. How do I put things together? How do I make a conjecture? Well, sometimes it's you build special cases. If you were the supreme being and you were creating the universe, and you want followers to love you and pray to you and sing songs unto thee, what would you choose for the product rule? If you're going to be a benevolent God. Yes, the derivative of a product is the product of the derivatives, and the derivative of a quotient is well, the related thing. You're not going to have the derivative of a quotient, the product of the derivatives. The derivative of the quotient will be the quotient of the derivatives. We're not going to need a huge stone tablet for that. It's going to be easy to remember, right? That's not what the rule is. So one thing that I think this would make a wonderful outreach article is to talk about how do you sniff out formulas. And so we'll do it for the product rule, and then we'll do it for something in probability. And so I need a function whose derivative I can calculate easily, another function whose derivative I can calculate easily, and I need to be able to calculate the derivative of their product easily. So can you give me 2 functions that are easy to differentiate, whose product is easy to differentiate?
Like function that's constant 1.
Okay, 1, and what else?
E to the x.
Okay, so I could do 1 and e to the x. But then, no, that's fine, but that only gives me really the function e to the x. But you can get some information from that, and we will do that. So it's not entirely a wise-ass answer. That will be used. But I want a little bit non-trivial. So can you give me 2 functions?
So you can do x squared and then like ln x.
But then you need to know the derivative of x squared times ln of x.
Yeah.
Can you do that without the product rule? Probably not.
Or you can do x and 1 over x. Sorry, x and 1 over x.
You could, but then you need to know what's the derivative of 1 over x, and that involves the reciprocal. You could prove by brute force what 1 over x has as its derivative, yes. But I think there's something easier.
X and x.
So you could do x and x. What else could you do? You could do x and x. What else could you do? X and 1. We have a 1 fetish today. Okay, yes, we could do x and 1. What else could we do? X and x squared. What else could we do? Give me another. Similar to x and x squared, we could do x and x cubed. So a really good, we could do f of x is x to the n, g of x is x to the m, and then f of x, g of x is x to the n plus m. And this way I can do a huge number of cases all at once by just choosing values of n. So I can now do your one by just taking n to be 0, right? But this allows me to handle lots of cases simultaneously. What's f prime of x? Nx to the n minus 1. G prime of x is mx to the m minus 1. And f of x, g of x, whole thing primed is n plus m x to the n plus m minus 1. So what I want to do is I want to somehow get the derivative of the product in terms of these 4 constituent functions. Now, before I do this, do you have any thoughts on the product rule? Thoughts on the shape of the product rule? What can you tell me? What properties should be true? Good. It should be symmetric in F and G. And now if we go back to the wise asses who used 1, what should happen if, say, f of x equals 1? What should you get? Right, good. So if f of x equals 1, you get g prime of x. If g of x equals 1, you should get f prime of x. How could I view g prime of x? So if f of x equals 1, you get g prime of x. How should I view that g prime of x? Yeah, so view as 1 times g prime of x here. Or maybe, what might you guess? So it is 1 times g prime of x, but what is 1 in this case? F of x. Maybe there's a term like f of x g prime of x, and then view as 1 times f prime of x here, or maybe f prime of x times g of x, just writing it in that order. And note, if f of x equals 1, if f of x equals 1, then f prime of x equals 0. So g prime of x would be f of x g prime of x plus f of x prime g of x. So all of this suggests maybe the derivative of a product, maybe it's f prime of x g of x plus f of x g prime of x. And it does work for x to the n and x to the m. Is this a proof? Not even close. But it suggests what the right formula is by looking at some special cases. We know it should be symmetric. If we take f of x or g of x to be 1, it reduces to something we already know. And then in this case, I need to get an n plus m, x to the n plus m minus 1. Is maybe a good way to view this is this is n, x to the n, x to the m, x to the minus 1, plus m, x to the n, x to the m, x to the negative 1. Trying to figure out ways to combine them. And you can start to see, oh, if I want to get something to the power n plus m minus 1, I want to be multiplying this way or that way. Can you come up with other examples where we can take the derivative of the product? Anybody give me another example where we could do it? Yeah, we could do e to the ax and e to the bx and the product is e to the a plus b of x. Why is the product e to the a plus bx? So why is e to the ax, e to the bx equal to e to the a plus bx? Okay. I agree with you that that's how exponents work, but this is not a question about exponents. What we really have is exponential function of ax times exponential function of bx. That is the sum, n goes from 0 to infinity, x to the n over n factorial, sum m goes from 0 to infinity, ax to the n over n factorial, bx to the m over m factorial. So if you want to prove that the product of two exponentials is the exponential of the sum of the, I'll say, exponents in quotes, it's really proving a statement about a double sum. And so as a nice exercise, try to prove this. And it can be done, you have to do a little bit of your convergence arguments to justify this. But there is some subtlety here if you want to use that as your example. If this were not the case, then we would have terrible notation. And we should have good notation. This is a class in mathematical writing. The goal is not to see how much content can we do when we meet. The goal is to talk about how can we do things well? How can we do things in such a way that people can follow what we're doing? You want to think about the notation you're using. There is notation that I truly despise in trigonometry, even though I understand where it comes from. Does anybody know, you have an advantage if you've taken a class with me in the past, what notation I don't like in trig? Cosecant. It bothers me, right? What do you think cosecant should be related to? Cosine, right? Shouldn't cosecant be 1 over cosine and secant 1 over sine? Does that bother anyone else? Not going to change it, right? We do, if you prove the Riemann hypothesis, maybe you can convince the mathematical community to follow you. Even then, I doubt it. There is a reason why cosecant goes with sine and secant goes with cosine. I don't like the reason, but I understand it. You want to think about what notation are you using and why. As soon as you write something like e to the ax, you should be thinking it's like raising a number. But really, the only way we understand this, and we talked a little bit about this in the first class, is through an infinite sum. There is one more example where we can actually do the product rule. The last example we could do is we could do sine of x, cosine of x. So this will be f of x. This will be g of x. And then f of x, g of x is sine of x, cosine of x. Does anybody know a nice way of writing sine of x, cosine of x?
Sine 2x over 2.
Sine 2x over 2, or 1/2 sine of 2x. So I'm going to assume that I know the multiple rule. The multiple rule isn't that bad to prove. It basically says if you replace x with c times x, then the derivative is increased by a factor of c. And so now we get f prime of x is derivative of sine is cosine of x. G prime of x is minus sine of x. And the mnemonic I like to use is you have to remember where to put the minus sign. It's minus sign. That's where the derivative goes. And now f of x, g of x prime is going to be 1/2 derivative of sine is cosine 2x times 2 is cosine 2x. So if you put everything together, does this look right? So f prime of x, g of x, plus f of x, g prime of x, which is what we're conjecturing from before, that's going to be minus sine squared x plus cosine squared x versus cosine 2x. And does anybody remember the trig expansion for cosine 2x? You don't have to remember, right? We know the product rule is true. So this has to be, except we write it as cosine squared x minus sine squared x. You know, it's cosine, cosine minus sine, sine. So if you remember your trig formulas, this becomes another non-trivial test of the product rule. And so the goal is to try to sniff out equations to get a sense of what you should try to prove. So let me give an example from probability. No, they're down here. Okay. So probability example. What should the probability of A union B equal? Can you tell me what it might involve? What could be constituents? Probability A, probability of B, anything else? Probability of the intersection. So hopefully something like that. And you know, the proof, of course, is not too bad if you know this is A over here, and you know this is B over here, and then this is A intersect B. Then the probability of A union B would be the probability of A plus the probability of B minus the double counted region. Let's try to sniff out a formula. So the probability of A union B should be maybe some function of the probability of A, say alpha times probability of A, plus beta times the probability of B, plus gamma times the probability of A intersect B. That's the simplest thing that we can think of that involves all of these. Can anybody give me any properties the probability of A union B should have? Good, so we should still have symmetric. So by symmetry, we have the probability of A union B is the probability of B union A. So what can we deduce? Alpha equals beta. And so now what we can do is we can start forming a table. Here is the probability of A. Oh, sorry, let's do it this way. Here is A, here's B, probability of A, probability of B, and then alpha probability of A plus alpha probability of B plus gamma probability of A intersect B, and then the probability of A intersect B. So the hope is that if you choose good items for B as a function of A, we should be able to compute everything. So what's a good choice for B?
Empty set.
Empty set. So if B is the empty set, let's let P be the probability of A. What would be the probability of B? 0. And then alpha probability of A plus alpha probability of B plus alpha probability of A intersect B, what would that be? So what would it be? I'm sorry? Alpha P. And what's the probability of A intersect B? You've got to be in both A and the empty set. Nothing's in the empty set. And the probability of A intersect B. Oh, sorry, there should be A union B on the end. Sorry, my apologies. And what should the probability of A union B equal? It should just be P. So therefore, what does this tell us? Alpha is 1. This doesn't prove that alpha equals 1. It just proves if there's a relationship like this, the only possible value of alpha that could work is alpha equals 1. That's not bad from just taking one simple test. So I love extreme cases. So continuing extreme mathematics, what could you do for B next? Nope. It's a good choice. Nothing It's a great choice, but I want to do extreme. The universe, everything, right? So we could take B to be everything. And then in that case, what's the probability of B? 1. And now we get alpha probability of A, but we know alpha is 1. So we'd get P plus 1 plus, now what's the probability of A intersect B if B is everything? So you get gamma P, right? And what is the probability of A union B if B is everything? Just 1. So what can you deduce here now? Gamma is -1. Did we prove gamma equals -1? No. But isn't this wonderful? By just looking at these extreme cases, we have a really good sense of what's going on. The only thing that would work is probability of A plus the probability of B minus the probability of A intersects B. Okay, now we'll do your suggestion of let's take B to be A. So we get P plus P minus P. Does that equal P? Yes, it's consistent. Oops. Come on. So it's consistent. I claim there's one more case that you should look at for B. Anybody think of the last case? Yeah, complement. So you could take A complement. So what's the probability of B if B is A complement? 1 minus P. And then we would get P plus 1 minus P. Now, what is A intersect A complement? 0 minus 0. And what's A union A complement? Everything, so that's 1. So it's consistent. So this is not a proof. But boy, does it seem to suggest that this is the answer.
Would it have been a proof if we knew that it has to follow this form?
Yes. So if you know it has to be of this form, then this would work. And so related to that, in calculus, what does it mean for a function to be differentiable at a point? Well, let's make it a little bit easier. What does it mean to be continuous at a point? So what does it mean for a function to be continuous at a point?
Full definition, like the delta epsilon definition.
You could do that. You could be a little bit more informal. So if my function is continuous at x naught, what does this mean? So as I approach that point x naught, so as x approaches x naught, what must be true? So f of x converges to f of x naught. So if you continuous at a point, as you converge to that point, then the value of your function has to converge to f of x naught. Now you had asked if we knew that it was of this form, would this now be a proof? Yes. If we knew it had to be of this form, and we show that this is the only form that works, now we're done. So one of the ways we could use this is imagine I know a limit exists. Then I can calculate the limit along any path. What path should I take? Hopefully a path that leads to an easy calculation. It's possible to come up with examples where the limit depends on the path. If people want, I can try to do this on the top, on the spur of the moment. Should I try? Yes or no? Great. That was the one. All right. We'll see if we can do it. So limit depends on the path. So an easy example is, let's say we have x squared plus y squared over x squared plus, oops, plus y to the fourth. If x equals 0 and y goes to 0, what do we get? So maybe we should do it the other way around. Let's do it the other way around. Let's do it y to the fourth upstairs and y squared down below. So if x equals 0 and y goes to 0, what do we get? For the function. Does everybody agree we get 0? So this would then just be the limit as y goes to 0 of y squared is 0. If y equals 0 and x goes to 0, this is the limit as x goes to 0 of 1, which is 1. So here's a nice example of a function where I get a different value depending on how I do things. A more interesting example, again, almost surely I'm not going to get this right in the spur of the moment, but what's bad about this example? You know, I'm approaching along two lines and I get different answers. Is this hard for a Calc 3 student to do? So what is the incorrect theorem Calc 3 students typically use to show that the limit exists?
Oh, it approaches the same value along two paths that exist.
Right, so along two paths, or which set of paths? Axes, right? So can I come up with something that has a limit along axes, but not along non-axes? So let's look at x squared plus y to the fourth over x squared plus y squared. Where is this bad? It's bad when y equals 0, right? So let's subtract x to the fourth plus y I want to do it this way. Okay, what if I looked at something like this? X to the fourth plus y to the eighth over x to the fourth plus y to the fourth. What happens if we approach along the axes? Yes, if we approach along the x-axis, we get 0. And if we approach along the y-axis, we get 0. Right? So here's an example where if we approach along those axes, we get 0. What if we approach along the line y equals x? So if go along y equals x, we get, what does the first one become? Becomes x squared plus 2x to the fourth over 2x squared minus x to the fourth plus x to the eighth over 2x to the fourth.
Was it 2x to the fourth?
Because if y equals x, then y to the fourth is just x to the fourth.
Oh, yeah. Top the numerator.
Oh, sorry, that should just be x to the fourth. Sorry, thank you. And we just take the limit as x goes to 0. So what would we get here? So we get 0. So along the line y equals x, we get 0. So we haven't made any mistakes, correct? Instead of doing the line y equals x, what else could we try? We could try y equals 2x, or more generally, I'm sorry? mx, right? Let's handle a lot of cases simultaneously. So this is the advantage of doing something like this. How do I change things if I put in y equals mx? This would become an m to the fourth x, right? And then down below, what would I get? I'm still going to have an x squared, but what's the coefficient going to be now? It's going to be 1 plus, I think, m squared. For the other one, I'm going to get a m to the eighth, x to the eighth up top. And then down below, I'm going to get an x to the fourth. And the coefficient is going to be 1 plus m to the fourth, I think. Is the limit still going to be 0? So do we agree now that the limit is not 0? So it was a fluke because m equaled 1. So if you tried this line, or you could even try the line negative x, that would also work. Those would also give you zeros. So my challenge, modify so limit is 0 along any line, any parabola, but fails for at least 1 cubic. Do you think such a thing exists? So the question is, can we modify things a little bit so that things aren't so bad? What would you try to change? I think I know what I would change. Well, so, again, I love teaching classes that are not the prerequisite for any other class, because it means we don't have to cover anything in particular. If there's something that you find interesting or something that I find interesting, we can explore it more. If I seem to be really excited, it's probably good for you guys to either be excited or act like you're excited and just roll with it. Or if not, just, if enough of you are just rolling your eyes, I should hopefully, get the point. But I seem a little bit excited right now. So whenever something is failing, you want to try to figure out what's causing the failure. Why did the limit break down? And this is actually color-coded for your benefit. Where was the issue? I'm sorry, the m's. And why were the m's different? What was responsible for the different m's? Yeah, the different m's from different powers. So which powers do we think were causing the trouble? We've got a bunch of exponents here. There's 8 of them. How many exponents at a minimum need to be involved in the problem? For things not to be equal, at a minimum, how many exponents have to be playing some role? Is it possible that it's all due to just one exponent? Can one exponent be preventing everything from being equal?
Wait, are we still approaching on the line y equals x?
Yeah.
So we're not talking about any other limit. We're
Right,
just
and so
approaching
so if you take m equals 0, you get the line y equals 0. It doesn't give us the line of x equals 0.
Well, you can divide this y by something like Like on the y equal to 4, you can modify it like y as something like y
Right,
equals
right. So
4.
good. So you're talking about exponents to modify. Is it possible that I only have to modify one exponent? Is it possible that every exponent is fine and one exponent is wrong? There should at least be two exponents involved, because if I'm getting a difference, it's got to be, this is giving me something different than another exponent. So the question here is, which exponents seem to matter? What do you notice about the two sides?
One exponent that's raised to double the power of the other one.
Yeah, so they have one that's raised to the double power. So is it important that it's double the power? Could I have done y to the 10th rather than y to the 8th? Yeah, that's not going to make any real difference. The issue that's coming in, and it's so much fun to have all these colors, is I've got an m to the 4th and an m squared. Those are coming in as different things. So I would need to somehow adjust things somehow so that these would become the same. And so, perhaps the simplest thing is, what if I modified it to x squared plus y to the 4th over x squared plus y squared minus x squared plus y to the 8th over x squared plus y squared. Would that work? If we now tried, y equals mx, we take the limit as x goes to 0, we would have, for the first one, we would have x squared plus m to the 4th, x to the 4th. Well, when x is small, that doesn't really matter. And the bottom would be 1 plus m squared, x squared, minus x squared plus m to the 8th, x to the 8th, over 1 plus m squared, x squared. What would that equal? 0. Did we solve the problem? Now it's equal to 0 along lines. I mean, doesn't it seem like we've done something good? What does this equal?
One to the 4th minus 1 to the 8th over.
Yes, I mean, it's really just y to the 4th minus y to the 8th over x squared plus y squared. So it's just a fancy way of writing that and coming to that. Do you think that this is going to have the same behavior along parabolas? So again, let's build some intuition. What's a good parabola to try? We could do that, or we could do a little bit more general, so we could do a lot all at once. So again, this is one of the things I want you to get out of this class. For many math problems, it's nice to have a free parameter that you can play with, so that you can do lots of cases at once and then specialize. It's not bad to do y equals x squared. That's the simplest one. So we either want y equals x squared, or what's the other thing we could try? I'm sorry?
X squared.
Right, but that's one possibility. Y equals x squared, y equals mx squared. What's the other possibility? Nope. What's the other parabola to look at?
Equals ny.
Yes. Or x equals ny squared. Right? I don't know which one is better. Maybe they're both fine. But those are the two natural things to try. The simplest possible parabola. And if we feed that in for the first one, if we take the limit as x goes to 0, if we take y equals mx squared, then we're going to get the top is going to be x to the 4th. So it's going to be m squared plus 1 x to the fourth, and down below is going to be x squared plus m squared x to the fourth. What's that going to go to? So all of those parabolas, it's going to go to 0. For the other one, we get the limit as y goes to 0. Oh, sorry, that was just the first term, sorry. And then we have the second term. Sorry about that. And then for the second term, do we see that it's going to be a similar argument? It's also going to be 0. So I'll just say similar, and that's also going to be 0. All right. Let's look at the other one. We would have the limit as y goes to 0. What's the first thing going to be now? We would have x equals ny squared. So we would have n squared plus 1 y to the fourth. Over down below, we're going to have y squared plus n squared y to the fourth. Or did I make a mistake?
No,
Oh, is the second one?
first term.
I'm sorry?
The very first term.
Yes.
I don't think it's x to the power of 4 because we have y to the power of 4 and then we just have to do the quadratic x. So it's going to be y to the power of 8. Sorry, x to the power of 8 somewhere.
That should be x squared plus.
Oh, sorry, yes. I made a mistake in a place where it doesn't matter, but yes.
Yeah.
So the first one would be x squared, and then it would be m to the fourth x to the eighth. Yes, thank you. Oh, so wait a minute. Oh, so if that's the case, then what is that looking like? That's looking like 1 now, right? Okay, so then that looks like 1. And then the other one should also look like 1. And when we subtract, it should be 0. If we do it the other way, if we take x to be ny squared, the first one is going to be y to the fourth. And then down below, it will be y to the fourth plus y squared. And then the second one would be n squared y to the fourth plus y to the eighth over n squared y to the fourth plus y squared. If I'm using y equals, if I use x equals ny squared, did I do that correct? And what would I get in this case? So so the first term is going to be 0, and the second term is going to be 0. So this would be something that would be 0 over 0 along quadratics, at least along pure quadratics. Is it possible that I would eventually get something where it would not be this? So I'll leave this as a challenge for you. I would suggest probably something in the form x to the a1 plus y to the b1 over x to the c1 plus y to the d1 minus x to the a2 plus y to the b2 over x to the c2 plus y to the d2. Maybe something of that form should work. There aren't that many choices to try for the exponents. Could probably even write a computer program to search for this.
I mean, eventually, I think it's just, the denominator, like the x squared term is gonna dominate everything. Because
So you start to look for which one dominates and when.
Yeah, so I think it's eventually it's all zero, unless there's edge cases.
Right. And so then the question is, do I want to have something like x squared plus y squared where they're the same degree? Or do I want maybe something like x squared plus y to the fourth? And now, if x equals my or y equals mx, then they're not going to be of the same size. But if I did a parabola, an x squared and a y to the fourth could become the same size. So maybe the problem is I don't want things to be of the same exponent in the denominator. Maybe I do want something like an x squared plus y to the fourth. So I'll leave this for you as to, can you search and find an example? I will let you know that there is an example. I remember creating this when I was teaching multivariable calculus, because I figured if I came up with something where the limit was 0 along any line and any parabola, y equals mx squared or x equals ny squared, that would be more than enough for every student to say the limit exists. But it fails along cubics. So it is possible to do that. You could probably come up with one that's true along all straight lines, but fails along parabolas. So as a nice challenge problem, find such an example and think about the thought process of how you would find the example. So to some extent, the homework is not just to come up with the problem or to solve the problem, but to think about how would you get there. Okay, what I want to do is I want to talk about one of my favorite problems. Pythagorean triples, kind of. Everybody should know about triples a squared plus b squared equals c squared. Can somebody give me the canonical example? Yeah, 3, 4, 5. You got to say 3, 4, 5. Can somebody give me another example? Good. So that is the smart-ass example. You can do any number alpha times 3, 4, 5, right? And you've just given me infinitely many more examples. So we often talk about primitive Pythagorean triples where no number divides them all. So what's another one?
1, 12, 13.
I'm sorry?
1, 12, 13.
1, 12, 13.
5,
5, 12,
yeah,
13. Yes. 5, 12, 13 works. So it turns out that there's infinitely many of them. And so here's one question. Does a squared plus b squared equals c squared plus d squared equals r squared infinitely often? Does a squared plus b squared equals c squared plus d squared infinitely often? And what do I want to assume about a, b, c, and d in order to make this interesting? Can you give me infinitely many pairs such that a squared plus b squared equals c squared plus d squared? Yeah, if I take a equals b, c equals d, right? So I want, say, a less than or equal to b and c less than or equal to d and p is distinct. If I don't do something like that, then it's really not that hard to find infinitely many pairs such that a squared plus b squared equals c squared plus d squared. And I'm not going to be that excited about finding such pairs. So in problems like this, you often want to remove the trivial solutions. So we're removing trivial solutions. And so this is related to one of my favorite, basic number theory problems. And we did this actually in 331 last semester. So this should look a little familiar to one of you. And so the question is, how can we do this? Well, one thing is to try to come up with an explicit formula of a quadruple that will work. And to try to play some games and to try to use some elementary number theory. What I want to do is I want to do some kind of high-level argument to show that this must happen. And I think this would make a wonderful math outreach paper. So it's related to some really good number theory. Can every integer be written as a sum of 2 squares? So what do you think? Do you think every integer can be written as a sum of 2 squares? So for example, if this is n, here's n squared. 0, 1, 2, 3, 4, 5, ... 0, 1, 4, 9, 16, 25, ... And if you start looking at all possibilities, sum of two squares, just gathering some data, we get 0, 1. What's the next thing we can get? What's the next sum of two squares we could get after 1? 2. What's the next one we can get? 4. What's the next one we can get after 4? 5. What's the next one? 8. What's the next one? 9, 10, 13, right? So the question is, which numbers can we get? Do you notice anything about these numbers? 0, 1, 2, 4, 5, 8, 9, 10, 13. So you can't get 3 mod 4. Cannot get 3 mod 4. And the reason is x squared mod 4. Is everybody familiar with mod arithmetic? Yes. So x squared mod 4 is either 0 or 1. So x squared plus y squared mod 4 is 0, 1, or 2. So we can't get anything that's 3 mod 4. Do we get everything that's not 3 mod 4? Okay, so give me something that's not 3 mod 4 that we don't get. 6. So sadly, 6 is not 3 mod 4, and 6 is not a sum of two squares. Well, maybe the problem is that 6 is a small number. That maybe if our numbers were larger, then every sufficiently large number is the sum of two squares, so long as it's not 3 mod 4. But there could be a few exceptions in the beginning. Well, the next number after 6 is 10. That's not, if we just add 4, that would be the same congruence class. We get 10. Can we get 14? No. So the question is, do you think that you can get every number that's sufficiently large? Or do you think that maybe we know that there's the difference between a necessary and sufficient condition? If anybody's ever seen the movie Dodgeball, there's a great line that just goes to my, okay, no one's seen Dodgeball. Just because something happens doesn't mean that the consequence you want, that's the difference between a necessary and a sufficient condition. It's necessary that our number is 0, 1, or 2 mod 4, but we've just shown it's not sufficient. It may be sufficient for all sufficiently large odd numbers. So let's look a little bit more intently. So let's consider a squared plus b squared less than equal to x. What can you tell me about a and b? If I want a squared plus b squared to be less than equal to x, what can you tell me about a and b? Less than equal to square root of x. So let's study the sum. A goes from 0 to square root of x. And then how large can b get? If I want a squared plus b squared to be at most x, given a, how large can b get to? X minus a squared square root. And I can count all of those pairs. Right? What's the first sum approximately? How big is the first sum? B goes from 0 to the square root of x minus a squared of 1. That's approximately the square root of x minus a squared. Now I have to evaluate that sum. How would you handle a sum like that? Yeah, make this into an integral. So maybe this is kind of like an integral of, let's say t goes from 0 to the square root of x of the square root of x minus t squared dt. Anybody have a thought of a change of variable? Try t equals, it should be screaming at you. So t goes from 0 to square root of x. We have an x minus t squared. Nope. There's an, no, you may want to get there eventually. But look at the x and the t squared. How could I try to get x and t squared to be of comparable size? I could write t as,
Square root of y.
I'm sorry,
Square root of y.
not quite square root of y. So my change of variable for t should involve x. T is going from 0 to square root of x. I have an x versus a t squared. If I let t equals something,
Oh, do we want to scale it down by square root of x?
yeah, what if I put in a square root of x over here? Then I have x versus x u squared, and I can pull out a square root of x. So then dt would become root x du. T goes from 0 to root x, becomes u goes from 0 to 1. And this now gives us the integral u goes from 0 to 1, the square root of x minus x u squared dt is going to be square root of x du. I can pull out an x from the square root of x minus x u squared, and then that should just be x times the integral from 0 to 1, the square root of 1 minus u squared du. And notice this is independent of x. So the fraction of numbers I get is going to be less than 1. That is not the most pleasant of integrals to do, but I know it's less than 1 because the integrand is at most 1, and it's less than 1 over large regions. And now we can use our trig substitution. We can have all those joys of trying to evaluate this elementarily. No one's going to do that. What are you going to do when my back is turned? Mathematica, right? Or Wolfram Alpha if you don't have Mathematica on your device, right? This isn't that bad of a thing. Anybody have a thought about what you might try to do for your change of variable? Maybe try sine theta. And then that should give you like a 1 minus sine squared, which would be a cosine. Then the derivative of sine will be a cosine, so you get like a cosine squared. And there's actually a trick to integrate cosine squared. Integrating cosine squared is the same as integrating 1/2 of cosine squared plus sine squared. So integrating cosine squared over a full period or a half period is not that bad. This is not a horrible integral to do. So there are ways to estimate this. And by doing this, we will get a nice answer for what fraction of numbers up to x can be covered. And we'll see that the fraction is less than 100%. So this is enough to prove less than 100% of numbers are covered. If I try to do this quickly, the integral of 1 minus u squared du, integral u goes from 0 to 1. All right, so I said u equals sine of theta, du is cosine theta, u goes from 0 to 1, theta goes from 0 to 1, 0 to, pi halves. Yes. And that's why you use sine, not cosine. So this integral should equal, the integral theta goes from 0 to pi halves. 1 minus u squared becomes 1 minus sine squared becomes square root of cosine squared becomes cosine theta. It's positive because it's the positive region. Du is cosine theta d theta. This is the same as 1/2 the integral. Theta goes from 0 to pi. Let's just do it 0 to pi. If I want to go all the way up to 2 pi, I divide by 4. Is everybody comfortable with that? Cosine squared theta d theta. This is the same as 1/8 integral theta goes from 0 to 2 pi of cosine squared theta plus sine squared theta d theta. What does the integral equal? Pi over 4. So it's 2 pi over 8 or pi over 4. And pi over 4 is approximately, unfortunately, I think 75%. Damn. We know that you can't get any number that's 3 mod 4. That's 25% of all the numbers. So is it possible that all the numbers we don't get are in that 25%? Yeah, unfortunately. Another way to see this is what we're really doing is here is a circle of radius square root of x. And what we're looking at is we're looking at all pairs of A and B inside a circle of radius square root of x. And you want to count what's the area. So I know Professor Goldmacher has talked about this in some of his classes. There's a beautiful formula that the number of lattice points in a shape should be essentially the area. And then you hope that the error term is a power smaller. And this is the famous Gauss circle power. Just how much smaller is it? Okay, so this is unfortunately not enough. But what we were doing here is we were looking mod 4. What else could we do? Look mod 8. And so if we look mod 8, we have until 35 passed, right? Okay, so we have n is 0, 1, 2, 3, 4, 5, 6, 7. N squared is 0, 1, 4. 9 is 1. 0, 5 is the same as 8 minus 3, right? So when I square it, it's really the same as 3 squared. So the pattern just goes in reverse, right? I don't have that much time. I've got to be fast, guys. So now if I look at x squared plus y squared mod 8, I can get 0, I can get 1, I can get 2. Can I get 3? No. Can I get 4? Can I get 5? Can I get 6? Can I get 7? Can I get 8? Yeah. So I get 1, 2, 3, 4, 5. I get 5 of 8. Or 5/8, which is approximately what? 62.5%? Now that's better. So we've now shown that it's not going to be as much as 75%. We're going to get at most 62.5%. So we know we have to be missing a lot more than just the numbers that are 3 mod 4. So my question is, what's the best modulus to use? You can keep using powers of 2, and what you'll see is that as you use powers of 2, you get closer and closer and closer to 50%. Is there a modulus that actually gets below the correct things? I might actually be off by some factor here. So I'll send you the videos to look at from when I did this in 331. This would be a great write-up to do for Math Outreach, is can we find a modulus to look at, which will be enough to show that a positive % of the time, we have to have this kind of collision. If there are too few congruence classes, then things have to be colliding. If we have a lot of possible congruence classes, it's possible that everything is separate. All right, so this is a good place to stop.